All right. Thanks again, Eden. It's a great pleasure to be with everyone today, and thanks for the invitation to give this talk. So, just to kind of give you an overall of the goal of the work in my lab, we focus on developing interventions that would improve function after neural injury and disease and prevent secondary complications that result from the loss of mobility. And what I'd like to be doing over the next 15 minutes or so is share with you the range of technologies we use for restoring mobility after neural injury or disease, and particularly focusing on spinal cord injury. This will be a show and tell to give you an overall flavor of the work that we do. So just to tell you a little bit about myself, I got my undergraduate degree in electrical engineering and my PhD in biomedical engineering. I then did a postdoctoral fellowship in rehabilitation science, followed by a postdoctoral fellowship in neuroscience. And what I do is I bring these disciplines together to develop interventions for improving function. And our approach to all our interventions is that to first gain a deep understanding of the mechanisms of the injury and of motor control, and then develop a technological solution or a rehabilitation paradigm that improves functional outcomes. But before I start telling you about our work, I would like to acknowledge the incredible group of researchers that I've had the great privilege of working with over the past decade. We are the SMART network at the University of Alberta, and SMART stands for Sensory Motor Adaptive Rehabilitation Technology. And members of the SMART network come from many different disciplines. And these include neuroscience, engineering, computer science, rehabilitation, social science, and consumer needs. And really the mission of the SMART network is to develop intelligent medical devices and innovative rehabilitation interventions that significantly improve functional outcomes for people with neurological conditions. And our goal is to take these innovations to the clinic to improve quality of care and patient outcomes, while also reducing healthcare costs. And we're really been very excited about the SMART network because it has provided us with an ecosystem for accelerating discovery and its translation into practice and eventual social impact. I would also like to acknowledge the outstanding team of trainees and support staff in my lab who make our work possible. Without them, we can't do any of the work that I'm going to show you. Now, the work in my lab, as I said, focuses on restoring mobility and preventing secondary complications. And we do that by using wearable and implantable technologies and rehabilitation paradigms that enhance neuroplasticity. And what I'm going to do over the next few slides is show you examples of the wearable technologies we use, show you an example of an implantable technology that we have developed to restore standing and walking after severe paralysis. And I'm going to show you an example of a rehabilitation paradigm that enhances neuroplasticity and improves mobility. So one of the things that we do is we work with exoskeletons. And this particular exoskeleton is a commercially available exoskeleton, but our focus is to develop intelligent control strategies that improve the flexibility and the compliance of the exoskeleton while maintaining safety and stability of the user. This work we do very much in conjunction with Dr. Mahdi Tabakoli from the Faculty of Engineering. Now, we also develop our own exoskeletons. This is now an exoskeleton for the upper limbs, and the goal of this exoskeleton is to be able to assist persons with upper limb weakness in their activity of daily living. This exoskeleton has components that are hard and components that are soft, and is controlled by a smart strategy that detects the intention of the person and assists them as needed and performing tasks like lifting. And these objects that are being lifted over here are quite heavy, usually use, possibly both hands to do it. And someone with upper limb weakness would not be able to move these objects. Just to give you an example of what kind of exoskeletons we work with. This, again, work is in collaboration with Dr. Mahdi Tabakoli. Now, another thing that we're very interested in is understanding the neural mechanisms responsible for cooperative bimanual arm movements. And what you're seeing over here is the kin arm exoskeleton that we use for this work. This exoskeleton has 2 arms, and it allows you to do uncooperative and cooperative bimanual arm movements. It allows you to do a single unimanual, arm movement, either for the left or the right. And our goal is to use the learnings that we get from using this exoskeleton to develop motor control-based rehabilitation strategies for improving bimanual arm movements after neural injury or disease. Now, most upper extremity rehabilitation in this work that we're doing over here. Now, in addition to lower and upper limb exoskeletons, both for rehabilitation assistive devices or for basic science, we also develop electrical stimulation-based wearable technologies to prevent secondary health complications that result from the loss of mobility, as I mentioned. And these secondary complications include pressure injuries. And pressure injuries were used to be called the pressure ulcers in the past and bed sores. And probably you guys are familiar with these. These are really gaping open wounds that develop in persons who are unable to move. And the soft tissue just breaks down all the way from the skin to a new intelligent garment called the sock, or smart ongoing circulatory compressions to prevent the formation of deep vein thrombosis. So switching to the implantable technologies and rehabilitation paradigms for improving walking after spinal cord injury, our approach here has focused over many years on harnessing the networks in the spinal cord itself. And I'll first show you a snapshot of our work in activating the networks in this region of the spinal cord that you see on the left. And then I will also touch on our work in activating networks throughout the cord, as you see here on the right. Now, for persons with severe spinal cord injury, we have focused on activating the networks in this region. This is called the lumbar region. It's a region that is just at the base of your back, and it's only 5 centimeters long. But the reason we, something that's very interesting is that this region usually remains intact after spinal cord injury because most of the injuries are either at the thoracic or the cervical levels. What happens to this region is that it no longer receives connections or commands from the brain. So the reason we focus on this region is because it contains all the motor neurons or all the nerve cells that control the muscles of the lower extremities. It also contains a large proportion of the neural networks involved in locomotion. In other words, this is the spinal control center for locomotion. And our goal has been to tap into these networks to produce functional overground walking. Now, we've done quite a bit of work to try to understand where the locomotor networks reside within the spinal cord. And we found that they reside deep in the cord, as you can see here marked by the blue regions. Now, of course, what you're looking at is a cross-section of the spinal cord. You see the back is on top and the front is on bottom. And you see the classical butterfly shape of the gray matter surrounded by the white matter, and then surrounded by the different meningeal layers, the pia mater, the arachnoid, and the dura mater. Now, with the locomotor networks residing deep in the cord, the question became, how do you activate them? How do you reach them? So one way to do that is to use epidural stimulation. And in epidural stimulation, electrodes that you see indicated here by green and black are placed on the surface of the dura mater. And then electrical fields generated by epidural stimulation penetrate about, they stimulate the dorsal roots and they penetrate about 200 to 300 microns within the dorsal surface of the cord. But this then indirectly activates the regions of interest deep in the cord. And exciting recent work that used epidural spinal cord stimulation in people with severe spinal cord injury showed that in conjunction with about a year and a half of intensive locomotor training therapy, 3 people so far with motor complete injuries were able to step over ground for distances up to 91 meters. This was just incredibly exciting because these people were not able to walk at all previously. So this duration and distance of walking is quite a great achievement. And it showed us that the locomotor networks are alive and well, even after severe spinal cord injury. But the challenge was that this stepping does not meet the clinical guiding principles for functional walking over ground. So perhaps there's only one person over here who may be able to walk independently using a walker, but for short distances. So our thinking was perhaps activating the locomotor networks more directly through penetrating microelectrodes that you see here in green can produce much more effective functional walking. Now, we call this approach for activating the locomotor related networks intraspinal microstimulation or deep spinal cord stimulation. And conceptually, you can think of this as being similar to deep brain stimulation that has been effectively used to treat various conditions such as Parkinson's disease. So in my lab, we developed a micro implant to be placed in the lumbar enlargement, which is this very small region over here, and to deliver the microstimulation. And the implant, which you see magnified many, many, many times over here, consists of microwire electrodes, smaller than the human hair. These are 50 micron in diameter. And you have leads that connect those microwire electrodes to an implanted stimulator that is accessed wirelessly. And conceptually, with this micro implant that is again placed in this, very small region, is expected, and blown up over here, is expected to activate various elements of the locomotor networks in a coordinated fashion, such that this would result in functional overground walking. So we tested this implant in several preclinical models. And what I'm going to show you here is an example of the walking outcomes that was achieved. This figure shows the force that's generated over 1,000 meters of walking, or a whole kilometer of continuous walking. And this walking was all generated by those intraspinal microstimulation wires, this micro implant in the spinal cord. And you can see that the generated forces are stable throughout this distance. And this distance of walking is truly unprecedented, especially when you compare it to other approaches, including epidural spinal cord stimulation, seen here in the red dashed line, where walking decays after about 100 to 150 meters. So with intraspinal microstimulation, it seems like we can generate walking distances that are 10 times longer than what is currently possible. So these results, along with many other results that we have obtained over the years regarding safety and feasibility of the implant, have now convinced us that we need to prepare this microimplant for clinical translation. And that's where a lot of our effort is dedicated right now. Now, in the last portion of my talk, I'd like to share a rehabilitation paradigm that can improve walking in persons with less severe spinal cord injury or persons experiencing other neurological conditions such as stroke or multiple sclerosis. And for these conditions, we propose that engaging the arms along with the legs in an activity-based therapy is what's needed for improving walking, because that allows for the engagement of networks throughout the spinal cord. And we really believe that this engagement throughout the spinal cord is what's really needed for effective walking in various neurological conditions. Now, there's plenty of evidence for the engagement of the arms during walking. We already know that the arms swing in coordination with the legs during walking, and this swinging is not the result of the arms behaving as passive mechanical appendages. Instead, arm swing is neurally driven, and the neural drive to the arms is coordinated with the drive to the legs. Now, this information has been around for many, many years, and a number of investigators have suggested that the arms can modulate the motor output of the legs. However, the arms have not to date been systematically involved in activity-based therapy for improving walking, and most therapies, as you see over here, focus on the legs only. So we wanted to investigate whether engaging the arms simultaneously with the legs does lead to functional improvements in walking, even after chronic spinal cord injury. So to deliver the intervention, we decided to use simultaneous arm and leg cycling as an activity-based therapy that is efficient in terms of the number of physiotherapists who need to be utilized. And this intervention allows coordinated rhythmic activation of the arms and the legs. And we applied electrical stimulation to the legs during training to assist with the generation of the movement. And this electrical stimulation also sends sensory input to the spinal cord in a phasic manner during the movements. And this coordination between motor and sensory input is very important for inducing neuroplasticity. And what's really very exciting is what we found out is that this efficient way of engaging the spinal networks throughout the spinal cord was very effective in improving walking capacity. And these videos that you see are from here, over here, are from a study participant before and after training. Now, before training on the left, you see he's walking slowly, he's hunched over, he's having difficulty in swinging his legs. And he's really, he's really using all sorts of biomechanical compensation to walk. But post-training on the right, you see that he's standing upright, he's walking much faster than before, and he is no longer needing to look at his feet because he now has restored sensation that allows him to know where his legs are in space without needing to look down. Also, the spasticity that was quite high in his legs has disappeared. So this, very interestingly, the improvements in walking capacity with arm and leg cycling were actually at least 2 times greater than the improvements gained with current rehabilitation interventions. And what this has demonstrated is that engaging the networks throughout the spinal cord is very important for walking and very much important for inducing better neuroplasticity. So this was now a show and tell and a snapshot of all the work that we do in the lab. So to wrap the talk, I hope that I convinced you that technological solutions are addressing unmet medical needs. I've shown you how we're making exoskeletons more intelligent so that they can be more compliant and more adaptive to the user needs. I showed you that we are developing exoskeletons that will help and act as assistive devices during daily living. And I also showed you that we have smart textiles that can prevent secondary complications. I also showed you that engaging the spinal networks is an effective means for improving walking after spinal cord injury. Microimplants in the spinal cord can activate inaccessible spinal networks related to locomotion, even after severe spinal cord injury. And I showed you that the arms play an important role in the rehabilitation of walking. So with that, I'd like to close by thanking the funding agencies and donors for their generous support, without which we would not have been able to perform this work. And thank you.